In this video, I want to look at the maths behind matrices and linear transformations. This gets rather abstract and is really rather more intended for the adventurous amongst you. So if you would rather not watch this video, that's fine. Just consider it as an optional extra. Let's look first at something nice and easy, multiplication. If I have three numbers to multiply together, I could either multiply the 3 and the 2 first, or I could multiply the 4 and the 3 first. In the top line, we get 4 times 6, which is 24. And in the bottom line, we get 12 times 2, which is also 24. This doesn't work if we look at division. Let's try 12 divided by 6 divided by 2. If I do the 6 divided by 2 first, I'm not going to get the same answer as if I do the 12 divided by 6. The top line gives me 12 divided by 3, which is 4. And the bottom line gives me 2 divided by 2, which is 1. And they're not the same. We can talk about multiplying three numbers together, but I don't think you've ever heard anyone talk about dividing three numbers together. In exactly the same way, we can add three numbers together, but we can't subtract three numbers together. Well, when we start talking about matrices, can we do the same thing? If we have three matrices, L, M, and N, does it matter whether we do M times N first or L times N? If our three matrices are as shown in the diagram, then we would first of all multiply the two matrices for M and N together. So we would do EF times IK, and then EF times JL. And now we multiply everything by A, B, C, D. Well, that wasn't too bad, was it? Now what happens if we switch the brackets round? What happens if we do L, M first, and then multiply by N? Let's see if we can do this one a little faster. And now we can see that if we take the top line, which is L times Mn, and the bottom line here, which is Lm times N, let's just look in detail. We've got AEI, we've got AEI, we've got AFK, we've got AFK, we've got BHK, we've got BHK, and we've got BGI, we've got BGI. Second one, AEJ, AEJ, AFL, AFL, BGJ, BGJ, BHL, and BHL. So you could check the other two, they're on the screen for you. And in this we can see that LM, if we do LM first, it is exactly the same as doing Mn first. And we say that matrix multiplication is associative. You don't need to know that word, but that is the mathematics that we have. Now, what do we mean by a linear transformation? Well, here I have a very abstract definition. T is a linear transformation on a set of vectors if T of k times x vector is k times T of x vector for any number, any real number k. And secondly, that if T of x plus y vectors is T of x vector plus T of y vector. for any vectors in that set. Well, let's look at one or two examples to see what this means. Let's first look at the idea that t of x, y is equal to 3x, 3y. So we start with the point xy, we finish with the point 3x, 3y, or vectors, whichever way you like to think of it. Does this satisfy our condition A? Well, let's look at t of k times xy. Well, k times xy is kx, ky, and t, the transformation t, tells us to multiply the top part by 3 and the bottom part by 3. So let's do that. That gives us 3kx, 3ky, which I can write as k times 3x, 3y, which is k times t of xy. And so condition A is satisfied. What about B? Let's look at t of vector x1, x2 plus y1, y2. Well, we know how to add vectors. That is just t of x1 plus y1, x2 plus y2. T tells us to multiply the top one by 3 and to multiply the bottom one by 3. Well, it doesn't take much to split that up as 3x1, 3x2 plus 3y1, 3y2, and that is just what we would get if we did t of x1, x2 multiply top and bottom by 3, and the second one is just t of y1 plus y2. So condition B is satisfied. In this case, t is a linear transformation. Okay, let's look at another one. Let's suppose we take the transformation t to be t of xy equals x minus 1, y plus 2. That looks nice and easy, and as if we ought to be able to think of that as a linear transformation. Let's see if it works. Let's look at the condition A. T of k times xy is equal to t of kx, ky, and this transformation tells us to subtract 1 from the top number and add 2 to the bottom number. So let's do that. Subtract 1 from the top number and add 2 to the bottom number. So there is t of kxy. What happens if we look at k times t of xy? That is going to be k. T of xy is x minus 1, y plus 2. And if we multiply that through, we get kx minus k, ky plus 2k. And now we can see that we've got different answers. So it doesn't satisfy the first condition that t of kxy has to be k times t of xy. So in this case, t is not a linear transformation. So there's an example. One is a linear transformation, one isn't, just satisfying this definition that I have put up as to what a linear transformation is. One general result and that is that T of 0, 0 is always mapped onto 0, 0. Well, I'm going to prove this by contradiction. Let us assume that T is a linear transformation and that T of 0, 0 equals A, B, where A and B are not both 0. Let's look at condition A. T of k times 0, 0 is equal to T of, well, k times 0, 0 is 0, 0, and that therefore is A, B. Let's look at k T of 0, 0. That is k times A, B, which is Ka, Kb. And this is supposed to be true for all real numbers k. And if A and B are not both 0, this cannot be true. So we now have a contradiction. Therefore, my assumption is false. Therefore, T 0, 0 cannot be mapped onto AB where they're not both 0. Therefore, it can only be mapped onto 0, 0. We now show that any matrix represents a linear transformation. Let's take the matrix M, A, B, C, D. We first need to show that the matrix M times K times the vector xy is K times M of xy. And so the first condition for a linear transformation is satisfied. For the second condition, we need to show that M of x1, y1 plus x2, y2 is M of x, y1 and plus M of x2, y2. And so the second condition for a linear transformation is satisfied. And so we have proved that any matrix represents a linear transformation. In particular, let's take any matrix times some point, let's say 3, 4. We can think of this as M times 3 times 1, 0 plus 4 times 0, 1. Because M is a linear transformation, this must be 3 times the image of 1, 0 plus 4 times the image of 0, 1. And so if we know the images of 1, 0 and 0, 1, we know where any point in the plane actually goes. It can also be shown that any linear transformation can be represented by a matrix, but that is another story. You will find the textbook treatment for this on pages 82 to 85 of FP1. And if you want to strengthen your understanding, you should do questions 1 to 4 of exercise 4D.